everyone, it's Alejandro. Welcome back for day 362 of me doing Daily LeetCode Challenge at 31 years worth of contributions here on GitHub. So today's problem is for July 13th, 2025, and without further ado, let's get straight into it. Okay, today we get LeetCode problem 2410, maximum matching of players with trainers. It's a maximization problem, which means we're probably going to need either DP, greedy, or divide and conquer, since this is a type of optimization problem. For reference, as a quick little update, as always, I still have, my broken little leg. I have it on a little bit of elevation here, and we're just going to try to make do. I'm just hoping that I can do this LeetCode problem today as quickly as possible so that I can go to the rooftop and start doing another set of 10 heel slides and 10 quad isometrics and 15 ankle pumps, just so that I can keep getting the blood flowing over and over and over. You might see me sweating a little bit in the face just because it is really, really hot here right now. And obviously I can't really leave the room, which again, another reason I'm hoping to go to the rooftop. But for now, let's solve this beautiful LeetCode problem. All right, you're given a zero-index integer array players, where players of I represents the ability of the ith player. You're also given a zero-index integer array trainers. Okay, so players of I represents the ability, trainers of J represents the training capacity of the jth trainer. The ith player can match with the jth trainer if the player's ability is less than or equal to the trainer's training capacity. Additionally, the ith player can be matched with at most one trainer, and the jth trainer can be matched with at most one player. Return the maximum number of matching players between players and trainers that satisfy these conditions. There's like heights and paddles, except like here there's no error function. It's just how much can you do, right? Like it's just going to be one of those where it's like you can't. I'm guessing you can't do it in n squared time. Yeah, they're both into the 5. Yeah. So it's like, you essentially want like the you want the trainer with the smallest capacity to go to the player that can, like one way of doing this usually greedily is like, sorting both and then just matching one by one, right? Are they both the same length? Oh no, they're not necessarily the same length, right? Yeah, they're not necessarily the same length. Right, where it's like, what you do is like, you do like players.sort, right? This is like heights and paddles problem, trainers.sort. And it's like, you have I, j is equal, I equals j equals 0. For player and players, right? These are sorted in frequency of smallest to lowest. Just say index is equal to 0. Equals trainers of index. Index equal to the length of trainers. N, comma m equals length of players, length of trainers. Greater or equal to m, break. No more trainers left. All right, otherwise trainers equal to trainers of index. And we're going to say if less than player, trainer cannot train player. Oh yeah, here we're essentially going to say while trainer, here we'll say while index is less than m and trainers of index is less than player, here we're going to say assert index equals m, no more trainers left. Otherwise there is a trainer left. I'll say trainer we'll say so index can train player is weakest weakest player, next weakest player as name trainer. Hence, assign these as such, and continue the problem. We will say res equals index. We'll say res plus equal 1, x plus equal 1, right? And then return res. Something like what? No, I don't want the debugger. I just want it to run. Accept it. Submit. And there we go. Bada bing, bada boom. Completion streak 362 days. Consistency is key. See ya tomorrow. Very nice. Yeah, straightforward problem. This is basically just heights and paddles. You might. Okay, well, first of all, as always, in all my videos, I do a cookie cap of various little solid problems. So for this one, again, I was just saying, like, this reminds me of a problem called heights and paddles. Heights and paddles might not necessarily be a known algorithm. Just like generally, it's something that I learned in university. One of our homework assignments inside of our advanced algorithms class. Basically, our advanced algorithms class, CSE C73 at the University of Toronto Scarborough, we only covered how to solve optimization problems. So in this problem, we have to do maximum of something. This is a type of optimization problem. In our advanced algorithms class, we only focus on solving optimization problems. And we only learned 3 methods to solve optimization problems. We only learned greedy, divide and conquer, and dynamic programming. That's why I always say that we can usually rely on one of these 3 for optimization problems, just because of what I learned in university. That was the first half of the course. The second half of the course, we started doing problem reductions, learning maximum flow with Ford Fulkerson and all that fun stuff, yada yada yada. But in terms of purely solving optimization problems, those were the techniques. And the very first one we learned was greedy, and we had 2 or 3 assignments on greedy. We had 7 assignments throughout the entire year. Brutal assignments, by the way. And one of the problems was essentially this heights and paddles problem, where essentially you want to minimize error, where you have a bunch of players and a bunch of paddles, and essentially the price you pay, quote unquote, if you give a paddle to a person is their difference in height, right? If a paddle is 5 feet and a person's height is 6 feet, then you pay a price of 1. 6 minus 5, absolute value is 1, right? And then it's the total sum of all the quote-unquote prices or error or whatever is a total error or cost you pay, and this is something you want to minimize, right? In this case, this problem is a little bit more, brutal in the sense that where it's it's 1 or 0, not just some error function you're trying to minimize. It's either you can assign a trainer to a player or you cannot assign a trainer to a player, right? The way you solve the heights and paddles problem, by the way, is just you sort the paddles and you sort the heights, as you give the minimum height to the minimum paddle, second minimum height to the second minimum paddle in height, and yada yada yada. And you had to prove, right? In our advanced algorithms class, you had to prove why greedy algorithm was correct. I remember my friend Armando proved that one using the exchange argument and so on. So I actually didn't prove that one, but I just know it's a correct algorithm. And for this problem, so what I did is I essentially just sorted players and sorted trainers. And then I realized, okay, that way I can essentially keep track of an index for player and an index for trainer. And the way I can think about it is, let me go through all the players, right? I'm going to go through all the players from weakest to largest, right? The weakest player is going to be the one that needs the least tolerance, right? What I can do is then remain an index for the sorted trainers and say, hey, can the weakest trainer train this player? If not, okay, let's move on to the second weakest trainer. If not, move on to the third weakest trainer, right? And keep going until you're okay, this trainer can finally train this player, right? And then assign them as so and keep on going. So that's kind of the idea. Here I say n comma m is equal to length of players, length of trainers, sort players and trainers. Res is going to be my result. Index is going to be my trainer's index. And here's how we're going to do it. We're going to go through all the players from weakest to strongest, right? We're going to say, okay, let's keep this index starts at 0 and will only move forward, right? It will never move backwards. So we'll only end up traversing trainers a total of only 1 full parse, right? Inside of this for loop, right? It's not like we're going through all of the trainers array inside of every single element inside of players, right? Here we say, okay, well, index is less than m, and trainers at current index's value is less than player. That means the trainer cannot train this player. Now notice, since we're going through the players from weakest to largest, right? If the current trainer cannot train this current player, that means this current trainer can train no player, right? It cannot train any player. So we can essentially discard this trainer forever, because we know that this is the current weakest player we have, because we're going through them from weakest to largest, right? Where we sorted them here in ascending order. So we know if the current trainers at index is less than player, it's less than that player and every remaining player. So we can essentially kill off this trainer. We don't need it. So that's why we're going to say index plus or equal to 1. And we also say if as long as the index is less than m, because we want to keep in balance, right? If index is greater than or equal to m, that means we've gone through all the trainers, right? There's no trainers left to train any more players, so we're done. So we say, okay, assert index is equal to m, and just break out of the if statement here, right? So that way we can just return res. Or you could just put return res in here, that's written here, right? Otherwise, what happened? What happened is you exited out of this while loop, right? And it's not the case that index is greater than or equal to m, which means this must have been invalid, which means that trainers of index is greater than or equal to player, which means we finally found a trainer that is strong enough to train this player. Now, the only thing, like, yes, you could say, like, oh, can I find, like, the player stronger than this that could train it and so on, Doesn't really matter, right? Again, this is a greedy algorithm, and I just know, I just figured this idea would work thanks to, like, the heights and battles problem from back when I solved it in uni. I didn't write the exchange argument proof for that problem. My friend Armando did. But, I'm sure you could do some, like, promising set argument where it's like, okay, yes, you could find, like, a player that is maybe a little stronger and still, like, trainable by this trainer. And then it's like, this would have been an optimal solution, but, like, you could swap it, and here's why this is also an optimal solution. I'm obviously too lazy to do that, but I'm sure you could write a proof for why this is still correct. But nevertheless, what this means is, hey, we broke this, which means this current trainer is strong enough to train the player. So we're going to have this trainer train this player. We might as well, right? Instead of looking for, like, some player that is stronger but also trainable, it's like, might as well just train this player and then keep on moving through, because we have to use up this trainer, right? We might as well use up this trainer on some player, right? We might as well use it on this player, because any trainer that follows is going to be stronger than or equal to the current trainer, right? So if we're worried about giving this trainer to a stronger player, we don't have to be, because we know that any remaining trainer is only going to be greater than or equal in strength. So if this trainer could pick up a player that is stronger than this current player, well, so can the other trainer, because, again, we only have trainers stronger than the current trainer remaining, because, again, we also have trainers sorted, right? So that's kind of the idea. So we're going to give the current trainer, which is the weakest of all trainers that we currently have, to the current player, which is the current weakest of all players that we have, right? We have weakest remaining trainer, weakest remaining player, they match, make them match, and then keep on going with the problem. So we're going to say, hey, res plus or equal to 1, because we're making this current weakest remaining player trained by the weakest currently remaining trainer. So we say one more match has been created, and then move on, because it's like, hey, so now we're using this trainer. So let's augment index by 1 again, because we just used up this trainer. And then we'll go into the next iteration of the for loop, because, hey, we just matched this player, so we now ignore this player and move on to the next player, right? So that's kind of the idea. And that way, it's like, basically we're going to go through every single player, and we're going to say, like, okay, can the current weakest trainer train it, right? And if not, like, keep on going, keep on going, keep on going. And if no trainer can train it, then that's okay, because this is our current remaining weakest remaining player. So if no trainer can train that one, no trainer can train any remaining one, right? That's kind of the greedy part of this problem. We go through the players from weakest to the strongest, and with the trainers from weakest to strongest as well, right? And it's just like, keep on iterating until, like, a trainer is strong enough, break if there's no trainers remaining, otherwise give that current remaining weakest trainer to the current remaining weakest player, match them, and move on, right? Augment trainers index by 1, augment players index by 1, and keep on going with the problem. And we're going to essentially keep iterating this for loop over and over and over until we've matched, as many trainers and players as we possibly can, and then we'll return result. And as we can see, bada bing, bada boom, we have a nice and efficient working solution to this problem. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful, enjoyable, and able to perform, I'd highly appreciate if you left a like or comment. Otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.